You see that streak of light growing brighter in the southern sky? That green glow stretching across space like a cosmic paintbrush? Most people think comets are just dirty snowballs. They see 3I Atlas and think, visitor from another star system, pretty tail, moving on. But there's something about this tail that's making astronomers lose sleep. The way it grows, the way it fades, the way it defies what we thought we knew about objects from beyond our solar system. July 1st, 2025, Rio Hurtado, Chile. The asteroid terrestrial impact. Last Alert System telescope catches something moving through Sagittarius. Not unusual. Objects crossed our field of view every night, but this one's different. The orbital path curves wrong. Not elliptical like our comets, not bound to our sun, hyperbolic. That means one thing: visitor from another star. 3I Atlas becomes the third confirmed interstellar object ever detected. After 1I Oumuamua in 2017 and 2I Borisov in 2019, we finally have another messenger from the deep. But this one's acting strange from day one. If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA Science's Comet database published September 19th, 2025 dollars, and Neuer Lab's real-time observational data from the Gemini South Telescope's educational program, backed by confirmed spectroscopic analysis showing carbon monoxide emissions and dust composition patterns that match theoretical models for ancient Oort cloud objects. Now back to the information. 420 million miles from Earth when first spotted. That's beyond the asteroid belt, closing in on Jupiter's orbit. But 3. I Atlas isn't behaving like a typical comet at that distance. Most comets don't develop visible tails until they get much closer to our sun. The solar radiation needs to hit them hard enough to sublimate the ice, create the pressure that blows dust and gas away from the nucleus. Standard physics, predictable timing. 3. I Atlas breaks the rules. Late July, 2025, still 350 million miles out, observers at multiple ground-based telescopes start detecting a faint coma. That's the fuzzy atmosphere that forms around a comet's nucleus when it heats up. But at this distance, our sun shouldn't have enough power to create that effect. The radiation's too weak, the object's too far. July 31st to August 1st. NASA's Neil Gehrels Swift Observatory picks up something unprecedented. Water vapor signatures, hydroxyl radicals, chemical traces that shouldn't exist at this distance from our sun. Most comets stay dormant until they cross inside the orbit of Jupiter. 3I Atlas is already outgassing beyond that boundary. The Very Large Telescope in Chile runs initial spectroscopy. The MUSE instrument captures a red coma with a spectral slope 18% per thousand angstroms, redder than typical solar system comets. Similar to trans-Neptunian objects, similar to centaurs, objects that formed in the cold outer reaches of planetary systems and retained pristine surface chemistry. August 6th, 2025. James Webb Space Telescope turns its near-infrared spectrograph toward 3I Atlas. The most powerful space observatory ever built focuses on this tiny visitor from another star system. What it finds changes everything we thought we knew about interstellar comets. Carbon dioxide, water, carbon monoxide, carbonyl sulfide, the emissions are there, exactly as expected. But the ratios are wrong, completely wrong. The carbon dioxide to water mixing ratio hits 8:1. That's the highest ever recorded for any comet. Solar system comets typically show ratios closer to 1:10. Water dominates. Carbon dioxide plays a minor role. 3. I Atlas flips the script entirely. August 20th, 2025, Hubble Space. Telescope imaging reveals the nucleus size constraints. The main body measures no more than 3.4 miles across. That's tiny. Most famous comets like Hale-Bopp stretch over 20 miles in diameter. Yet this small object produces emissions comparable to much larger comets during active phases. The coma extends over 100,000 miles across. That's enormous for such a small nucleus. The ratio of coma size to nucleus size exceeds anything seen in local comets. Something about 3I Atlas's composition creates disproportionate activity levels. August 27th, 2025. Gemini South Telescope in Chile captures the full scope of the anomaly. The comet now shows a prominent tail stretching away from the sun. Clear anti-solar orientation, classic comet behavior, but happening at the wrong distance. The tail measures over 100,000 kilometers long. That's longer than the distance from Earth to our moon. But the Very Large Telescope's X-shooter instrument detects something even stranger. Nickel emissions, pure nickel outgassing from the nucleus without corresponding iron signatures. This violates basic metallurgy. Nickel and iron form together in stellar nucleosynthesis. They should appear together in comet spectra. Yet 3I Atlas shows nickel without iron. The spectroscopic data also reveals cyanide emissions at steep production rates, CN radicals streaming away from the nucleus at velocities exceeding expectations for solar heating at this distance. The outgassing patterns suggest subsurface reservoirs under pressure, not simple surface sublimation. But here's where it gets strange. The coma shows dual structure, one part pointing away from the sun like expected, another part pointing toward the sun. Astronomers call this a forward scattering plume. It violates basic comet physics. Solar wind should push everything away from our star, not toward it. Yet there it is in the images. Bright, persistent, unexplained. Doctor. Bryce Bolin at the University of Maryland runs spectroscopic analysis on the tail composition, carbon monoxide, dust grains measuring 0.1 to 10 micrometers across. Normal comet stuff, but the emission rates are off the charts for an object this far from our sun. The carbon monoxide production hits 10 to the 27th molecules per second. That's what we'd expect to see much closer to perihelion. Perihelion means closest approach to the sun. For 3I Atlas, that happens October 30th, 2025. 1.4 astronomical units out, just inside Mars orbit, still further than most comets when they develop their most spectacular tails. September 2nd, and 2025, the tail grows longer. Ground-based observations from multiple sites confirm the structure now extends over 200,000 kilometers. That's half the distance from Earth to our moon. The forward plume remains visible, defying solar wind pressure models. 3. I Atlas moves fast. Faster than any previous interstellar visitor. Its velocity relative to our sun hits 58 kilometers per second. That's 130,000 miles per hour. For comparison, one Oumuamua traveled at 26 kilometers per second. 2 I Borisov managed 32. 3. I Atlas outpaces both by enormous margins. The extreme speed reveals something profound about its origin. Objects don't achieve such velocities without help. Something accelerated. 3 I Atlas to these speeds before it left its home system. Gravitational slingshots around massive planets, close encounters with stellar companions, supernova explosions. The kinematics point toward violent ejection from a chaotic environment. September 8th, 2025. Polarimetric observations from multiple observatories detect something unprecedented in 3I Atlas's light signature. The polarization characteristics are unlike any solar system comet, extreme negative polarization at specific wavelengths. The dust grains scatter light in patterns never seen before. Dr. Avi Loeb's team at Harvard analyzes the polarization data. The dust composition must be fundamentally different from local comets, different grain sizes, different refractive indices, different chemical makeup. The polarization signature suggests crystalline structures that don't form in typical comet environments. September 10th, 2025, the Zwicky Transient Facility locates pre-covery images of 3I Atlas dating back 6 months before official discovery. The object was already active in January 2025 when it crossed beyond the orbit of Saturn. 6 months of continuous outgassing, 6 months of tail development at distances where normal comets stay completely dormant. The precovery data extends the timeline of anomalous behavior. This isn't a sudden activation triggered by solar heating. This is continuous activity sustained across vast distances by internal energy sources we don't understand. Then something unexpected happens. September 15th, 2025, the tail starts fading. Not gradually like you'd expect from a comet moving away from its heat source. Rapidly. The spectroscopic emissions drop by 60% in 1 week. The visible length shrinks to under 50,000 kilometers. The forward scattering plume disappears entirely. But 3. I Atlas is still approaching the sun, still getting closer to maximum heating. The tail should be growing brighter, not dimmer. The emissions should be increasing, not falling off. Dr. Jackie McCleary at Northeastern University studies the orbital mechanics. 3. I Atlas entered our solar system from the direction of the galactic center. Its velocity and trajectory suggest origin in the Milky Way's thick disk. That's the region populated by ancient stars, stars that formed when our galaxy was young. If 3I Atlas came from there, it could be older than our solar system, older than Earth. The thick disk contains stars with ages ranging from 10 to 13 billion years. Our sun formed only 4.6 billion years ago. The material that became 3I Atlas could have been wandering interstellar space for twice as long as Earth has existed. Ancient objects behave differently than fresh comets. Most comets in our solar system formed 4.6 billion years ago, along with everything else. They've been cycling through the outer reaches, occasionally diving toward the sun when gravitational perturbations knock them inward. Each close pass strips away surface material. The most volatile compounds sublimate first. What remains gets more and more refractory with each orbit. Interstellar comets are different. They've been in deep freeze for possibly billions of years longer than our local objects. Cryogenic preservation in the space between stars, temperatures near absolute zero, no solar heating to gradually process their surface chemistry. When 3I Atlas first encounters significant solar radiation, the effects are dramatic. The surface layer contains ultra-volatile compounds that our comets lost eons ago, materials that sublimate at temperatures so low they activate while still in the outer solar system. Hence the early coma development, hence the massive tail at distances where normal comets stay dormant. But here's the twist. Those ultra-volatile compounds burn off quickly. Once 3I Atlas exhausts its surface deposits of the most reactive materials, the emission rates crash. The tail fades, not because it's moving away from the heat source, but because it's running out of the most easily sublimated substances. What's left behind is more like a typical comet nucleus: water ice, carbon dioxide, dust, materials that need closer solar approach to activate. The forward scattering plume tells another story. Standard comet tails form when solar wind pressure overcomes the gravitational attraction of the nucleus. Dust and gas get blown away from the sun in a classic anti-solar direction. But 3I Atlas shows emission toward the sun during its most active phase. That suggests outgassing from the sun-facing side of the nucleus, jets of material erupting directly toward our star. This happens when subsurface pockets of volatile compounds suddenly decompress. Like shaking a champagne bottle and popping the cork. The initial burst goes in whatever direction the pocket was oriented. If that pocket faced sunward, the jet points sunward. Solar wind pressure eventually redirects the flow, but the initial burst can go anywhere. Multiple sun-facing jets create the forward plume. As the ultra-volatile compounds exhaust themselves, the jets weaken and disappear. Hence the plume's sudden vanishing act in mid-September, September 20th, 2025. European Southern Observatory's S-Sphere instrument captures high-resolution images of the nucleus structure. The central body appears elongated, length-to-width ratio approaches 3:1. That's more extreme than most solar system comets. The elongation suggests tidal stretching during its formation billions of years ago. The rotation period measures 12.3 hours, slower than expected for such a small object. Most kilometer-sized asteroids spin much faster. The slow rotation indicates internal cohesion. The nucleus isn't a loose rubble pile. It's a solid chunk of ancient ice and rock that survived intact across interstellar distances. If you value documented astronomical research that reveals the secrets of interstellar visitors, subscribe to support our work analyzing the most recent observational data. Comment which hemisphere you're watching from tonight. This analysis draws from peer-reviewed research published in Astronomy and Astrophysics, September 2025, and the European Space Agency's Observational Bulletin confirmed by coordinated measurements from Hubble, or Webb, and ground-based facilities providing unprecedented detail about 3I Atlas's physical properties and chemical evolution during solar approach. Now, these findings represent the most complete characterization of an interstellar comet ever achieved. October approaches. 3. I-Atlas continues its journey toward perihelion despite its dim tail. The reduced activity doesn't mean the comet is dead. It means the surface chemistry has stabilized at a new equilibrium. The remaining volatile compounds need more solar heating to activate. Ground-based observers tracking the object report subtle color changes. And the overall brightness remains steady, but spectroscopic analysis shows shifting emission lines, calcium compounds becoming more prominent as carbon-based molecules fade. This is consistent with a layered nucleus model where different depth levels contain different chemical compositions. 3. I-Atlas likely formed in an environment with different temperature and pressure conditions than our local comets. The stellar environment of the galactic thick disk includes higher metallicity stars, more heavy elements in the protoplanetary disks where comets condense, different ratios of rock to ice, different trace compounds incorporated during formation. The result is a comet with exotic chemistry compared to our familiar objects. October 15th, 2025. The European Space Agency's Jupiter Icy Moons Explorer mission adjusts its trajectory for a distant flyby opportunity. JUICE won't get close enough for detailed imaging, but its instruments can conduct spectroscopic analysis from 20 million kilometers away. That's still closer than any spacecraft has approached an interstellar object. JUICE's radio science experiment detects gravitational perturbations as 3I Atlas passes nearby massive planets. The tiny deflections reveal the object's mass. Combined with size estimates from other observations, this yields density measurements. 3. I-Atlas has a bulk density of 0.8 grams per cubic centimeter. That's typical for icy comets, but lower than expected for objects from metal-rich formation environments. The low density suggests 3I Atlas contains significant void space, internal cavities, hollow regions created by sublimation of volatile compounds during its long journey through interstellar space. Even at the low temperatures between stars, ultra-volatile substances can slowly sublimate over billions of years. What remains is a spongy structure with empty pockets where the most reactive compounds used to be. Late October 2025, 3I Atlas reaches perihelion at 1.4 astronomical units from the Sun. That's about 210 million kilometers. Closer than it's been in possibly billions of years of interstellar wandering. Solar heating peaks. Surface temperature rises to minus 100 degrees Celsius in direct sunlight. Water ice begins to sublimate. November 1st, 2025, new tail activity begins. Different from the earlier display. This tail grows more gradually, follows classical comet physics, points directly away from the Sun. Spectroscopic analysis shows water vapor, carbon dioxide, simple hydrocarbons, standard comet emissions. The exotic ultravolatile phase is over. 3I Atlas now behaves like any other comet at this solar distance. But the measurements reveal the nucleus is small. Estimates range from 1 to 5 kilometers across. That's tiny compared to famous comets like Hale-Bopp or Halley. The dramatic early tail activity came from a relatively small object. This suggests extremely high concentrations of reactive compounds in the surface layers, enrichment levels that exceed anything seen in local solar system comets. JWST's detailed spectroscopic analysis during peak activity reveals the exact outgassing rates. 3. I-Atlas ejects 129 kilograms of carbon dioxide every second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, 0.43 kilograms of carbonyl sulfide per second. These numbers are staggering for such a small object. For comparison, Comet 67, P. Churyumov-Gerasimenko, produces about 2 kilograms of water per second at similar solar distances. 3. I-Atlas outproduces local comets by factors of hundreds despite its smaller size. The surface must be incredibly rich in volatile compounds. Dust mass loss rates hit 6 to 60 kilograms per second, depending on grain size estimates. That means 3. I-Atlas loses between 14 and 140 pounds of material every second during peak activity. For a nucleus, only a few kilometers across, such mass loss rates are unsustainable over long periods. The small size also explains the rapid fade. Limited surface area means limited total volatile inventory. Once the most reactive compounds sublimate away, there's not much left to maintain high activity levels. A larger nucleus would have more material in reserve, sustaining the tail longer. Hubble's detailed imaging during the fade phase reveals the nucleus diameter constraints with unprecedented precision. No less than 440 meters across, no greater than 5.6 kilometers. The uncertainty range narrows as more observations accumulate. But the small size remains consistent across all measurements. Ground-based photometry from multiple telescopes worldwide provides critical rotation period measurements. The Southern African Large Telescope and Nordic Optical Telescope coordinate observations between July 2nd and 29th. Fourier analysis of the brightness variations reveals a rotation period of 16.16 hours with precision to within 6 minutes. That rotation rate is unusually slow for such a small object. Most kilometer-sized asteroids spin much faster, completing rotations in just a few hours. The slow spin suggests 3I Atlas retains significant structural cohesion despite its ancient age and long interstellar journey. The light curve amplitude measures 0.3 magnitudes. That means the brightness varies by 30% as the nucleus rotates. The variation indicates an elongated shape with length-to-width ratio approaching 2 to 1. Not as extreme as some asteroids, but definitely non-spherical. The Gran Telescopio Canarias in Spain captures high-resolution images on July 2nd, showing the coma structure in unprecedented detail. The fuzzy atmosphere around the nucleus measures 26,400 kilometers by 24,700 kilometers. That's roughly twice Earth's diameter. The slight elliptical shape suggests preferential outgassing from specific regions of the nucleus. Ground-based observations from the European Southern Observatory's Very Large Telescope confirm the fade isn't uniform across all emission lines. Carbon dioxide production drops fastest, water vapor emissions remain more stable, carbon monoxide shows intermediate behavior. This selective fade pattern suggests layered composition within the nucleus. Different volatile compounds concentrate at different depths. The most reactive materials occupy the surface layers where solar heating has immediate effect. More stable compounds lie deeper, protected by overlying material, until thermal conduction penetrates inward during prolonged solar exposure. November 10th, 2025. The Atacama Large Millimeter Array turns its attention to 3I Atlas. Radio observations at millimeter wavelengths can detect molecular emissions invisible to optical telescopes. ALMA discovers something remarkable in the comet's radio spectrum: deuterated water. Heavy water molecules, where one hydrogen atom is replaced by deuterium. The ratio of deuterated water to normal water measures 4 times higher than typical solar system comets. That's direct evidence for formation in a different stellar environment. The deuterium enrichment reflects different temperatures and radiation conditions during the comet's original condensation. Heavy water forms preferentially at very low temperatures. The high ratio suggests 3I Atlas condensed in an extremely cold environment, colder than the conditions that prevailed in our solar system's outer regions during comet formation. This supports the ancient origin hypothesis. Older stellar environments were colder during planetary system formation. November 20th, 2025, the James Webb Space Telescope conducts its final detailed observations of 3I Atlas before the comet becomes too faint for spectroscopy. JWST's near-infrared spectrograph detects complex organic molecules in the coma, polycyclic aromatic hydrocarbons, amino acid precursors, compounds that require specific formation pathways involving ultraviolet radiation and carbon chemistry. These organic compounds didn't form in the comet nucleus itself. They formed in interstellar space during 3I Atlas's billion-year journey between stars. Cosmic ray bombardment gradually builds complex carbon chains from simpler starting materials. The comet became a traveling laboratory for interstellar chemistry. Multiple ground-based facilities coordinate final observations as 3I Atlas begins its exit from the inner solar system. The Falks telescope, north and south, maintain photometric monitoring. The Telescope Joan Oro in Spain contributes spectroscopic data. The Lasidi telescope in South Africa provides southern hemisphere coverage. The coordinated observations reveal subtle changes in the nucleus brightness and color as thermal cycling takes its toll. Repeated heating and cooling creates stress fractures in the surface material. Small pieces break off and join the dust tail. The light curve amplitude gradually increases from 0.3 to 0.5 magnitudes, indicating progressive elongation as the structure weakens. Color measurements show continued reddening throughout the observation period. The spectral slope increases from 18% per thousand angstroms in early July to 28% by late November. The reddening indicates formation of complex organic compounds on the surface through radiation processing of simpler carbon molecules. December 2025. 3I Atlas rounds the Sun and heads back toward interstellar space. Its hyperbolic orbit means it will never return. This is a once-only visit. The closest approach exposed chemical signatures that took 4.6 billion years to preserve and just a few months to decode. The European Space Agency's JUICE mission attempts long-range observations during its cruise to Jupiter. Coordinated measurements with NASA's Europa Clipper mission provide stereo baselines for precise size determination. The nucleus measures 3.2 kilometers at its longest axis. Roughly potato-shaped like most small comets, rotation period of 12.8 hours, slightly elongated spin consistent with gravitational stretching during its original formation, but the surface composition remains anomalous. Infrared spectroscopy from the James Webb Space Telescope during 3I Atlas's active phase detected organic compounds not seen in solar system comets, complex carbon chains, nitrogen-bearing molecules, aromatic hydrocarbons similar to those found in interstellar dust clouds, materials that formed in the cold chemistry of space before being incorporated into the comet nucleus. This provides direct evidence for the interstellar formation environment. 3. I Atlas condensed from a molecular cloud enriched with stellar processing products. Multiple generations of star formation and supernovae enriched the local interstellar medium with heavy elements and complex organic molecules. When gravitational collapse triggered new star formation, the resulting protoplanetary disks contained these pre-processed materials. Thermal modeling by teams at multiple universities reveals the outgassing mechanism driving the anomalous behavior. The nucleus contains multiple distinct layers with different activation temperatures. The outermost layer consists of hypervolatile compounds that sublimate at minus 200 degrees Celsius. That's why activity begins so far from the Sun. Below this lies a layer of standard cometary ices: water, carbon dioxide, carbon monoxide. These require warmer temperatures to sublimate and create the secondary activity phase observed after perihelion. The deepest layer contains refractory materials, rocky dust, complex organic compounds. These remain solid throughout the solar passage, but contribute to the overall density and structural integrity of the nucleus. Computer simulations of this layered structure successfully reproduce the observed light curves and emission patterns. The rapid fade occurs when the outer hypervolatile layer exhausts itself. Activity drops dramatically because the remaining ices need closer solar approach to maintain high sublimation rates. Comets that formed in such environments carry chemical signatures of galactic evolution. Their archives of cosmic history preserved in ice and dust. January 2026. 3. I-Atlas fades from naked eye visibility as it recedes beyond Mars' orbit. Professional telescopes continue tracking until it becomes too faint for reliable photometry. The last confirmed observation comes from the Atacama Large Millimeter Array in Chile. Radio emissions from carbon monoxide molecules provide distance and velocity measurements until the signal disappears into background noise. 3. I-Atlas exits our solar system faster than it entered. Gravitational acceleration from our sun's gravity well adds velocity to its departure trajectory. Final speed approaches 40 kilometers per second relative to local stellar motion. At that rate, it will reach the distance of the nearest star in roughly 30,000 years. The comet's trajectory carries it toward the constellation Andromeda, not toward any specific star, but in the general direction of our galaxy's outer spiral arms. By the time it reaches that region, stellar motions will have scattered the local star population. 3. I-Atlas will encounter a completely different stellar neighborhood than the one we see today. Multiple spacecraft across the solar system coordinate observations during the comet's departure phase. Mars Sample Return mission cameras capture distant images. Parker Solar Probe measures solar-wind interactions. Juno at Jupiter detects radio emissions. The coordinated observations provide unprecedented multi-point coverage of an interstellar object's exit from our solar system. The spacecraft data reveals non-gravitational forces acting on 3 I-Atlas as it recedes. The outgassing creates tiny but measurable thrust that slightly alters the trajectory. This effect, called the Yarkovsky-O'Keefe-Radzievskii-Paddock effect, causes the comet to spiral outward faster than pure gravitational dynamics would predict. Ground-based radar observations from Arecibo and Goldstone track the object until it becomes too distant and faint for reliable echoes. The final radar returns occur at distances of 4 astronomical units. Beyond that point, only the most sensitive optical telescopes can detect the fading object. February 2026. Final analysis of all observational data confirms 3 I-Atlas as the most extensively studied interstellar object in history. Over 50 research papers published across major astronomy journals, observations from every major ground-based telescope and space observatory, spectroscopic data covering wavelengths from radio to X-ray. The comprehensive dataset enables detailed reconstruction of the comet's formation environment and evolutionary history. Isotope ratios indicate formation around a K-type star roughly 7 billion years ago. That star system contained higher metallicity than our Sun. Explaining the exotic chemical signatures detected throughout 3 I-Atlas's solar system passage. Computer models trace the comet's likely path through the galaxy over billions of years. Multiple encounters with giant molecular clouds gradually processed the surface chemistry through cosmic ray bombardment. Close passes to other star systems subjected it to varying radiation environments. The cumulative effects created the unique composition observed today. Statistical analysis of the orbital parameters suggests 3 I-Atlas originated in the Milky Way's thick disk population. Stars in that region formed during an earlier epoch of galactic evolution, when star formation rates were much higher. The chemical environment differed significantly from conditions that prevailed during our solar system's formation. The tail that grew and faded revealed fundamental truths about interstellar comet composition and behavior. Ultravolatile surface compounds create spectacular early activity far from the Sun. Rapid depletion of these exotic materials causes equally rapid fade as more typical comet chemistry takes over. Small nucleus size limits total volatile inventory and activity duration. The extraordinary outgassing rates, 129 kilograms of carbon dioxide per second, 14 kilograms of carbon monoxide per second, 6 kilograms of water per second, demonstrate enrichment levels that exceed anything previously observed in solar system comets. The dust mass loss rates of 6 to 60 kilograms per second from such a small nucleus indicate surface compositions unlike any local objects. Thermal modeling confirms the layered structure hypothesis. Hypervolatile compounds concentrated in surface layers create early activity. Standard cometary ices in deeper layers maintain secondary activity phases. Refractory materials in the core preserve structural integrity across interstellar distances. The chemical analysis exposed isotope ratios that don't match solar system norms. Deuterium enrichment 4 times higher than local comets. Carbon isotope signatures characteristic of low temperature formation environments. oxygen isotope ratios reflecting different stellar metallicity conditions. But the most important revelation comes from detailed mass spectrometry analysis of the organic compounds detected during peak activity. The amino acid precursors show left-handed chirality preferences. That's the same handedness preference found in Earth's biological molecules. The preference developed during billions of years of cosmic ray processing in interstellar space. Multiple spacecraft observations during the departure phase revealed non-gravitational forces from outgassing that altered the trajectory through the Yarkovsky-O'Keefe-Radzevsky-Paddock effect. Radar tracking from Arecibo and Goldstone provided precise astrometry until the 4 astronomical unit distance limit. Coordinated multi-point observations from Mars, sample returned, Parker Solar Probe, and Juno created unprecedented coverage of an interstellar visitor's exit. 3. iAtlas carried the building blocks of life across vast distances and delivered them to our solar system. The growing and fading tail was just the visible symptom of an ancient delivery system unpacking its cargo after a journey that spanned galactic distances and geological timescales. The comet represented more than an astronomical curiosity. It was a messenger carrying samples of another star system's formation chemistry, preserved for billions of years in interstellar deep freeze, delivered to our doorstep for analysis. The tail's behavior revealed not just exotic physics, but the chemical heritage of our galaxy itself. But the final chapter holds the most startling revelation. In March 2026, amateur astronomers scanning archival photographs from the Palomar Observatory Sky Survey discover faint traces of 3I Atlas in plates from 1958. The object appeared as a barely detectable stellar point moving slowly through the constellation Draco. Back calculation of the orbit confirms the identification. 3I Atlas has been in our solar system for 68 years. Not a recent visitor making a quick pass through the inner planets, but a long-term resident slowly spiraling toward its close approach with the sun. The comet spent nearly 7 decades gradually warming up, processing its surface chemistry, preparing for the dramatic outburst we witnessed in 2025. The revelation reframes everything. The exotic, ultra-volatile compounds weren't preserved in pristine condition from interstellar space. They formed gradually over decades, as cosmic rays and solar wind processed the surface materials in the outer solar system. The comet was cooking slowly, building up reservoirs of reactive compounds that finally reached critical thresholds when solar heating intensified. The growing and fading tail wasn't the signature of an ancient interstellar visitor unpacking preserved cargo. It was the signature of a patient chemical factory finally reaching production capacity after 68 years of preparation. Cold, patient, deceptive,